In this video, we're going to continue our discussion of functions and talk about how to analyze graphs of functions. Certain things like if the graph is increasing or decreasing, where the function is symmetric across the y-axis and the x-axis, all of that. We're also going to talk a little bit about what's called a piecewise function. So first we're going to start with our test for symmetry. So if we're going to try to test the graph of a function for symmetry, first let's talk about how to tell if the graph of an equation is symmetric about the y-axis. So to check if it's symmetric about the y-axis, we need to replace x with negative x. And if we do that and get the same exact equation, that means that it's symmetric with respect to the y-axis. This means that if you plug in a negative x for all of your x's and nothing changes, that if you actually graph the equation, it will look exactly the same on both sides of the y-axis. To see if it has symmetry across the x-axis, we do something similar. We're going to replace every single y with negative y. And if we get the same exact equation, then that means it's symmetric with respect to the x-axis, which means that it looks exactly the same above the x-axis as it does below. And our one other type of symmetry is symmetry with respect to the origin. So the graph of the equation is symmetric with respect to the origin if you do both of these things and you get the same equation. So you replace x with negative x, and you replace y with negative y. And if you get the same exact equation, then it's symmetric with respect to the origin. So we're going to do some examples. We're going to look at a couple different equations and see if it's going to be symmetric with respect to the y-axis, x-axis, or origin, or combinations of all of these. So our example. Determine whether the graph of the equation y equals x squared is symmetric with respect to the x-axis, y-axis, or origin. And I'm going to start by checking with respect to the y-axis first, only because it was the first one I listed when I was listing how we test it. So to test if it's symmetric with respect to the y-axis, we know we have to replace every single x in our equation with a negative x. And then if we get the same exact equation out of that, it means it's symmetric with respect to the y-axis. So I replace my x with a negative x, and then I can simplify this. Negative x times negative x is positive x squared, because the negative times negative is positive. So when I simplify this, I get y equals x squared, which is my same exact equation as before. So I know that this equation is going to be symmetric with respect to the y-axis if I were to graph it. Now let's do the same thing, checking the x-axis. And then we'll also check the origin. So to check the x-axis, we're supposed to replace every single y in our equation with negative y and see if we end up with the same equation as before. Well, my original equation had just a positive y by itself, so I'm going to solve this equation for positive y by multiplying both sides by a negative. And I get y equals negative x squared. Notice this is not negative x inside of parentheses squared. It's a negative x squared. So this is not the same equation that we had before. And so we are not symmetric with respect to the x-axis. Last one to check is the origin. To check for symmetry with respect to the origin, we change all of our y's to negative y's, and we change all of our x's to negative x's. And now we see if this gets us our same equation as our original equation. Well, we know negative x in parentheses squared is positive x squared. I still have my negative y, which is exactly what we had up here before. So we already know if we solve this for positive y, it's not going to be the same. So it's not symmetric with respect to the origin. So we tested all of the three cases, and we found out that y equals x squared is symmetric with respect to the y-axis only. So symmetric with respect to the y-axis only. That WRT that I wrote down there, that's just a shorthand for with respect to, just to save me some time writing. And a lot of you know what the graph of x squared looks like already. We all should. It's our parabola. And if you look at that graph, you can see that, yes, it is symmetric with respect to the y-axis. It's exactly the same on both the left and the right side of the graph. It's not symmetric with respect to the x-axis, because I don't have anything below the x-axis, but I have all of this stuff up above. And it's not symmetric with respect to the origin, which that was a little bit trickier to notice. It's more of a rotational sort of thing. If you think about taking your graph and flipping it over the x and the y-axis, that's what should happen to symmetry with respect to the origin. This does not satisfy that. Let's do another example. So we are going to determine whether the graph of the equation x squared divided by 4 plus y squared divided by 9 equals 1 is symmetric with respect to the y-axis, x-axis, or origin. And I'm going to start with the y-axis again. So remember to check if it's symmetric with respect to the y-axis. We replace all of our x's with negative x. So instead of x squared over 4, I'm going to have negative x in parentheses squared over 4. And I still have y squared over 9 and equals 1. And just like our last example, negative x in parentheses squared is the same as positive x squared. So this gets me positive x squared over 4 plus y squared over 9 is equal to 1, which is the exact same equation I started with. So we are symmetric with respect to the y-axis. Now let's try it with respect to the x-axis. With respect to the x-axis, we need to test this by changing all of my y's to negative y. So I get x squared over 4 plus a negative y squared over 9 equals 1. But just like we had with the negative x in parentheses squared, This negative y in parentheses squared is going to be positive y squared. So this gets me x squared over 4 plus y squared over 9 equals 1, which is the same equation I had to start with. So we are symmetric with respect to the x-axis as well. Now all that's left is to check the origin. For the origin, you're supposed to change all of the x's to negative x and all of the y's to negative y. When I do this, using our same algebra as before, I get x squared over 4 plus y squared over 9 equals 1, my same exact equation again. So this particular equation has a graph which is symmetric to the y-axis, x-axis, and origin. This actually is the graph of an ellipse. I'm going to quick sketch it for us just so you can see the symmetry. This is an ellipse that goes through the points here and up here. And you could see this by graphing it using your calculator as well. And you can see, well, my drawing's pretty bad, but if you actually look on your calculator or a graphing utility, you'll see it's symmetric with respect to the y-axis. It's the same on both sides, the same top and bottom. That's symmetric with respect to the x-axis. And if you do both flips, flip it across the y and across the x, it's still going to look exactly the same. That's symmetric with respect to the origin. So all we've talked about so far is symmetry for equations. Notice it hasn't said anything about it being a function or not, just equations. In fact, that last equation that we just checked was not a function because it didn't pass our vertical line test. But now we need to learn about some special types of functions. They're called even and odd functions. So a function f is called an even function if f of negative x equals f of x for all x in the domain. Now this should look a little familiar. It kind of looks like our symmetry that we just talked about. I'm plugging a negative x in for all of my x's, and I'm getting my original function back. So we know an even function is going to be symmetric about the y-axis. So symmetric with respect to the y-axis. And now let's define an odd function. A function f is odd if f of negative x equals negative f of x for all x in the domain. Now this one's a little bit trickier to notice how it's equivalent to one of our tests for symmetry, but odd functions are functions that are symmetric with respect to the origin. Just quick write that down up at the top. Odd functions are symmetric with respect to the origin. And now we're going to do some examples testing some functions to see if they're even or odd or neither. Not every single function is even and not every single function is odd. There are functions out there that are neither even nor odd. So our example is, are the following functions even, odd, or neither. And our first one is going to be m of x equals negative x to the fifth plus x to the third. And regardless of whether it's going to be even or odd, both of our definitions involve an f of negative x. So in order to find out if a function is even or odd, you have to find that function evaluated at negative x and just see if you get either the same result, which would make it even, the opposite result, which would make it odd, or something that's neither of those, which would be neither. So we're going to find m of negative x. Remember, that means to replace every x with a negative x. And be careful with all of these negative signs. So I have a negative x in parentheses to the fifth power, plus a negative x in parentheses to the third power. And now we have to try to see if this is the same exact function, or if it's the opposite of our original function, or what exactly is going on. So negative x to the fifth power is going to stay negative. A negative to an odd power is negative. But then I have another negative on the outside, which will make it positive. So I get positive x to the fifth. And this guy, negative x to the third power, it's an odd power, so it's going to be negative x to the third. Well, this is definitely not the same function I had before, but is it the opposite of what I had before? We can find out. If I factor out a negative, I will get negative x to the fifth plus x to the third. And inside these parentheses here, I have my original function. So this is equal to negative m of x. So I got m of negative x equals negative m of x. This means it's an odd function. Let's do another one. Next one, we'll have n of x equals x squared minus the absolute value of x plus 1. To find out if it's even or odd, we're going to plug in a negative x. So I'm going to get negative x in parentheses squared minus absolute value of negative x plus 1. And now we're going to try to simplify this algebra. So negative x in parentheses squared is positive x squared. Having a negative inside of absolute values, we have to think about what absolute values do. They take things and make them non-negative. So the absolute value of negative x is the same thing as the absolute value of positive x. And I have my plus 1. Well, this happens to be exactly equal to my original function. This is n of x. So I got n of negative x equals n of x. This means we have an even function. And let's just do one last example. How about the function p of x equals 2 absolute value of x plus x? And we're going to start by plugging in negative x to see what happens. I get 2 absolute value of negative x plus a negative x. Simplifying this, the absolute value takes care of that negative, so I get 2 absolute value x, and then plus a negative x is minus x. Is this equal to my original function? No, because of that minus sign. Is this equal to the opposite of my function? Also no. Because in order for this to be the opposite of my function, all of my signs would have to be opposite. And this 2 absolute value of x agrees with my original 2 absolute value of x. It's not the opposite of it. So this is neither. All right. So that is how we can tell if a graph is going to be symmetric with respect to y-axis, x-axis, origin, and if we're talking about functions, whether it's an even function or an odd function. Now we have to talk about some special functions that are called piecewise functions. The reason that they're called piecewise functions is because they're defined in pieces. Instead of just having one function rule for the entire domain, there are different rules depending on what x values you're using when you plug it into the function. So piecewise functions. And we're just going to dive right into it. It's the best way to learn how to deal with piecewise functions is just to work with them. So we're going to start right away with an example. We're going to evaluate a function for the given values of x. And here is what my function is. F of x equals x plus 7 for x that are less than -2. X squared for x that are between -2 and 1, including -2 but not including 1, or my function is equal to 3 when x is greater than or equal to 1. So piecewise functions look a little strange when you look at this. It's giving us 3 different rules for this particular function. It depends on what your value of x is to determine which type of rule you're going to use. So I'm going to leave my function written down here at the bottom and give us our problems to solve up at the top. So the first one we're going to find is f of -3. So in order to figure out f of -3, we need to know how to read this definition for our function. The way we do this is first look at what your input value is going to be. I have f of -3. So my x value is -3. So how we figure out what rule to use, you look at all of these inequalities and figure out where -3 fits. -3 is less than -2. So this tells me I need to use this top rule here, x plus 7, to figure out my function. So f of -3, I get to use that top rule, plug in -3 for my x, and get -3 plus 7, which is 4. Next one, let's try f of -2. So again, to figure out what f of -2 is, we have to look at what our x value is, -2, and figure out which inequality it matches. -2, we can see it shows up twice in here, but in my orange box, I have x is less than -2. But this middle one here, I include my -2 with that equals. So this means I need my second rule, x squared. So f of -2 is equal to that x value squared, which is 4. Last one, just to make sure we got it, let's find f of 4. So just like the other ones, we have to look to find where our x value fits. My x value is 4, and 4 happens to be greater than or equal to 1. So this means that my function is equal to 3. So f of 4 is equal to 3, using that last definition for my function. All right. So that's how you evaluate a piecewise function. You figure out where the input matches all of our rules here, and then pick the appropriate definition for f for that particular x value. Now let's practice graphing one of these. Graphing piecewise functions can sound a lot more difficult than it actually is. You basically get to just graph each piece, but you graph it all on the same grid. So let's graph. We'll start with this first piecewise function, f of x equals 2 for x less than or equal to -1, and negative 2x for x greater than -1. Let me put a grid up here for us. All right. So how we're going to graph this is we're going to graph both pieces of the function, but we're going to put it on the same grid. Now, normally I would do this all just in one color, but I'm going to graph them in 2 different colors just to emphasize where each piece is coming from. So let's do this first part of the definition. I'll graph it in green. It says f of x equals 2, which we know would be a horizontal line at y equals 2, for all of our x values that are less than or equal to -1. So I'm going to start here at -1. I know there's a point up here at -1 and +2. And I know that I have a horizontal line of y equals 2 for all of the x values smaller than that. So that means my horizontal line goes to the left forever. Now, just to really emphasize the point, if I was just going to graph f of x equals 2, this would be a horizontal line going forever in both directions. But this tells me that it's only equal to 2 for that select set of x values. It stops once I reach -1. Once I get past -1, so x greater than -1, we need to use this new rule, -2x. And one mistake I see students make a lot is they'll just start plugging in points, like they'll plug in 0, 1, 2, and like connect the dots on that side. But you're forgetting all of the infinitely many values between -1 and 0. So I would suggest that you still plug -1 into this one and just graph it with an open circle. So if I were to plug -1 into this definition here, I'd get -2 times -1, which would be +2. So I would have an open circle for the red graph at -1, +2. Now notice that my open circle landed directly on my filled in point from before. That happens sometimes, but not all of the time. So here's a point that would be on my graph, the hole for this red part. And I know that f of x equals -2x is a linear function with a slope of -2. So I can go down 2 and over 1, down 2 and over 1. And I'm going to do it one more time, down 2 over 1, just so my graph is nice and straight. And there is the -2x piece. So -2x is in red, 2 is in green. And really, the graph of the whole function is both of these pieces together. So imagine it all graphed in just one color, and that would be the graph of this piecewise function. Let's do another one that's a little bit more complicated, still not too terrible. So part B. Going to be a graph that has 2 pieces again. We have f of x equals the absolute value of x for x that are in between -4 and 2, including -4, but not including 2. And it's going to equal -x plus 2 for x greater than or equal to 2. So first thing I'm going to point out is this graph doesn't go on forever in both directions. The smallest x value in our domain is -4. But let's get this graph up here. this graph on here, I'm going to start by graphing that absolute value graph. We know absolute values look like a V shape. I have to make sure I'm only graphing it for the particular x values I'm given. So I'm going to do the absolute value part in green. I know -4 is included, so I'm going to put a solid point at my -4, +4. And I know the other endpoint at 2, it would be at 2, 2, but I have an open circle there because I have less than 2, not less than or equal to 2. The rest of this just looks like our standard absolute value graph. So I'm going to put a couple dots on here just to try to keep my line a little bit straighter. So I get my absolute value V shape, but I'm only using part of my graph. Now for my other piece, I'm going to do that in red. I have -x + 2 for x that are greater than or equal to 2. So just like I did on the last one, we are going to plug in that endpoint. I'm going to plug in 2 to this function definition and see what the point is. This time it's going to be a closed dot because I have an equal to included in that inequality. So if I were to plug this 2 in, I would get -2 + 2, which is 0. So this means I have a point at 2, 0, right here. Notice that that point did not fill in our circle this time, like on our last graph, but that's okay. This just means that this particular function has a break in it. It's not continuous. That's fine. Now the rest of this, I know -x + 2 is a linear function. It would have a y-intercept of 2, except that's not in this part of my function definition, so it doesn't touch the y-axis. It starts here and then has a slope of -1. So down 1 and over 1, down 1 and over 1, and so on, and it goes forever. So this was my -x + 2 piece. This was my absolute value of x piece. And I get a piecewise function that has a little bit of a break in it, and that's okay. This is a discontinuous piecewise function, and we're going to talk more about continuity in this course and also when you move on to calculus. We're going to talk about a very particular type of piecewise function now. It's called a step function. And it's called a step function because if you graph it, the graph looks like a set of steps, discontinuous steps. So our definition, a step function is a piecewise function whose graph is a series of discontinuous steps. And we're going to do an example of a step function. We're going to do an example of a very particular type of step function, evaluated at a few places, and then I'll show you what the graph looks like to emphasize what the step shape looks like. So our example of a step function is called the greatest integer function. So the greatest integer function, which is also called the floor function, is f of x equals this strange notation with an x in it. Now there are lots of different notations out there. This is one that is used sometimes. Another notation I've seen before looks like this. It's the same thing though, where this x in those weird brackets is the greatest integer that is less than or equal to x. So you can think of this function as taking your numbers that you input and rounding it down to the next whole number. So this is not rounding to the nearest whole number, it's just always rounding down to the number below it. The greatest integer less than or equal to x. That's why it's also called a floor function. You take any number and they're considering the floor, the whole number that's beneath that number. So continuing this example, for our function, the greatest integer function or floor function, we're going to evaluate a few different things. First, f of 1.7. Well, just using our notation, this is going to be a 1.7 inside of those strange brackets. But now we have to think about what those brackets mean. It's talking about the greatest integer that is less than or equal to 1.7. Remember, this is like rounding down to the nearest whole number. So this is going to be 1. Similarly, if I do f of 5.5, again, think of taking your input and rounding it down to the nearest number, the nearest whole number that's smaller than where we were. So this would be rounded down to 5. What if I plug in something like -4? Well, that's where that equal to comes in our definition. We want the greatest integer that's less than or equal to our input. -4 is an integer, so this is going to stay at -4. And just one more to really emphasize the point. F of -4.2. Well, that is the floor of -4.2. And we just have to be a little bit careful because it's negative. Rounding this down puts us down to -5. That is the negative number that is below -4.2. Now, let me show you what the graph of this looks like, just so that you have this step function image in your head. All right, so let's just think for a second about what this was like. I'm going to start with these numbers between 0 and 1. So if we're graphing f of x equals our greatest integer function, that is rounding all of our decimal numbers down to the nearest integer that is less than or equal to the input. So all of these numbers here between 0 and 1 would round down to 0. So I have a closed dot here at 0, 0. 1 would be equal to 1 using this function, but all of these other numbers would have an output of 0. For the numbers between 1 and 2, we get a similar thing. They would all get rounded down to 1. Numbers between 2 and 3 get rounded down to 2. And between 3 and 4 get rounded down to 3. And just to really push the point in here, I'm going to do some of these in the negative direction as well. All the same logic. And you can see these steps that are forming. So your greatest integer function is just one example of a step function. It forms all of these steps that you can imagine someone walking up. All right. Now, to continue our discussion on analyzing graphs, we're going to talk about when a function is increasing or decreasing or constant, what that looks like on the graph. So let's suppose that I is an interval in our domain. Contained within the domain of a function f. Then f is increasing on the interval I if f of x1 is less than f of x2 for all x1 less than x2 in I. So that's a technical sounding definition, but really, it's not that complicated. What this is saying is the graph of a function is increasing on the interval if when you read it from left to right, it goes up. So here's an example. On this interval I, my graph is going up from left to right, so it is increasing. That's what all of this is saying here. I have going from left to right, my function increases, it gets bigger as I move. We have a similar definition for decreasing. So our function is decreasing on the interval I if f of x1 is greater than f of x2 for all x1 less than x2 in I. And all that this is saying is when you look at the graph of the function and read it from left to right, the graph is going to be going down. So if this is my interval I, then a graph is decreasing if it's going down from left to right. And the last thing is f is constant on an interval I if f of x1 equals f of x2 for all x1 less than x2 in I. All that this is saying is when you look at your graph from left to right, it's not going up and it's not going down. It's just staying flat. Let me quick draw a sketch of what it would look like if it were constant. And then we'll do an example. So this is my interval I. A function is constant on that interval if it's not going up and it's not going down. It's just flat. Let's do an example where we are given the graph of a function and we have to find where it's increasing, decreasing, or constant. So use interval notation to write the intervals over which f is increasing, decreasing, and constant. And here is the graph of this function. And this graph would be given to us. of the graph of the function that would be given to us would look like this. Goes on forever on this side, and it stops at this point over on that side. So we want to find where it's increasing, decreasing, and constant. So let's start with increasing. So we want to know, where is the graph going up from left to right? You can see at the very beginning it starts going up. It's going up when x is equal to -5 until we reach -3. So that first piece would be -5 to -3. Does it go up again later? Yes, it starts going up again once we reach -1, and it goes up until we reach 2. So I have the two intervals, -5 to -3 and -1 to 2. And I put this U shape in between to say it's the union of those intervals. That just means the graph is increasing on both of those intervals. How about decreasing? Where is the graph going down? Well, once we reach x equals 2, that's where our graph starts going down. And then it goes down forever. So I get the interval 2 to infinity. And last, where is it constant? That's just asking where it's flat. That just happens on this little piece here between -3 and -1. All right, so all we have left for this particular video is to define what a relative maximum or relative minimum is and how we find those from a graph. So our definition. F of A is a relative maximum of F if there exists an open interval containing A such that f of A is greater than or equal to f of x for all x in the interval. This is a very complicated sounding definition, but it's really not that complicated once you know what it's saying. All this is saying is we have a relative maximum if, when you look really, really close to that particular point, that point is bigger than all of the points that are right near it. So let me just sketch that. Here's just a random curve. We would have a relative maximum right here, because if I look at points that are close to it, that point is the tallest point on the graph. So it's a relative maximum. These are also called local maximum. And we have a very similar definition for if it's going to be a relative minimum. So our f of A is a relative minimum the rest of the definition is the same, except we have to change this to f of A is less than or equal to f of x for all x in that interval. So we have a relative minimum down here, because when I look at all of the values near that point is the lowest point. So when we are doing problems involving relative maximum or relative minimum values of our function, there's something very important we have to keep track of. For a particular point, A, f of A, the x-coordinate is the location of the relative maximum or minimum. The y-coordinate is the actual value of the relative max or min. So we're going to do an example now where we are given a graph and we have to find the relative max and relative min, if they exist, of this graph. And it is possible, even though this example doesn't have this, but it's possible to have multiple relative maxima and relative minima. So for the graph shown, we're going to determine the location and value of any relative maxima or minima. And here is the graph. We have here's our graph, and we want to find the relative maxima or minima of this graph. So first, let's find the maximum. Looking at the graph, we can see that the maximum is this point here, because when I look close to it, it's the tallest point in that tiny little neighborhood around it. So our maximum occurs at x equals -2. That's our location. At x equals -2, we have a relative maximum of the y-coordinate, which is 3. So the value is 3, and the location is at x equals -2. Similarly, for the minimum, well, I can see this is my minimum here because in that little neighborhood, it's the lowest point on the graph. So the location is at x equals +2. We have a relative minimum of the value is my y-coordinate, which is 0. All right, and that's all that I have for this particular video. Increasing, decreasing, constant, relative min, relative max, all of those are things that are going to come back to you in calculus when you get there. So it's good to have a basic understanding of it now because it will get more complicated in the future. If you have any questions, you can feel free to drop them below, or if you're a current student of mine, feel free to come to office hours or email your questions and I'll be glad to help. I'll see you in the next video.